In the last video, I said that we would start looking at compounds that were a little bit more challenging than the ones that we had been looking at, specifically compounds that were charged. So let's take a look at what happens if we're dealing with a cationic compound. Okay, we'll start off with a very simple example, and that would be ammonium. Okay, so ammonium has a positive charge. Okay, and we say that, well, we can figure out the total number of valence electrons just like we did before by looking at each element. We have nitrogen with 5 valence electrons. There's only one of those. Okay, we have hydrogen with its 1 valence electron, and there's 4 of them, for a total of 9 valence electrons. Okay, what we have to do now is a very crucial part of the process. If the compound has a positive charge, that means that it is experiencing 1 less electron than it should have. Okay, so if it has a positive charge, we have to subtract 1 valence electron. Okay, so that gives us 8 valence electrons to place. And then, just like before, we continue on. And we can distribute the electrons. And again, we see 8 electrons being distributed evenly around the nitrogen. Okay, so that nitrogen has its 8 electrons, hydrogen each has its 2. And then there's one thing that's left, and that is we need to know where to put the positive charge. Now this is kind of it seems silly because really the positive charge is spread out over the entire molecule. But we have to calculate what's called formal charge. And formal charge is basically our feeble mind's attempt to try to justify where charge actually is. And it's just, well, it's something we're going to have to do here. So we can calculate the formal charge. Okay, so formal charge is equal to the number of valence electrons on that particular atom minus the number of non-bonding electrons, so lone pairs of electrons, minus the number of bonding electrons divided by 2. And actually that should be a plus. Okay, so the formal charge on an element or on an atom of a compound is going to be equal to the number of valence electrons that atom should have minus the sum of the number of non-bonding electrons on that atom plus 1/2 of the bonding electrons. So let's look at nitrogen. So we want to figure out the formal charge on nitrogen. Okay, the number of valence electrons that nitrogen should have is 5. Now if we look at the structure that we've drawn, we see that every one of the electrons that's part of nitrogen is involved in a bond. So there are 0 non-bonding electrons. Okay, plus, okay, the number of bonding electrons, we have a total of 8, right? 2 for each bond to hydrogen. So 8 divided by 2, and we get plus 1, which tells us that the nitrogen is what's carrying the positive charge from an electronic bookkeeping standpoint. We could have also done the calculation for hydrogen. Okay, and we expect then that the formal charge on hydrogen should be equal to 0, but let's make sure of it. Okay, hydrogen has 1 valence electron. There are 0 non-bonding electrons. Plus, now here's the tricky part. When we're doing the formal charge calculation, we're doing it for a specific atom, not for the element, so not for all hydrogen in the molecule, but we're picking a particular hydrogen. Okay, so that one hydrogen should have a single valence electron, Okay, and if I'm looking at it, it only has these two electrons, which are both bonding electrons. And we see that this gives us 0. Now, we could go through and calculate the formal charge for each one of these hydrogens, but there's not much point in doing that because we can see just by visual inspection that these are all equal to one another. They're all in the same situation. So they're all going to be 0. Okay, so that's how we calculate the formal charge. We can do the same thing for anions. Okay, so for the example of an anion, let's look at something a little bit more challenging. Okay, we can look at the nitrate ion. Now, nitrate, we have nitrogen, 5 valence electrons times 1. We have oxygen with its 6 valence electrons times 3. Okay, so we have 5 plus 18 gives us 23. Now we have a negative charge, which tells us the molecule has one more electron than a neutral molecule would have. So here we add an electron for a total of 24. Okay. Now, with the nitrate ion, there's actually a number of different ways that we could, in principle, arrange the atoms. So, for example, we could have had the 2 oxygens on one side of the nitrogen, one on the other. We could have had 3 oxygens on one side of the nitrogen. Or we could have had the oxygens each individually attached to the nitrogen. And you can't always tell just by looking which one's going to be correct. Now at this level, I would say that 9 times out of 10 you can get away with trying to choose the most symmetric structure, but that won't always work. So let's show what happens if we have a second structure that we're not quite sure about and we have to figure out whether it's right or wrong. So let's look at the one on the far left hand side. If we have 24 electrons, that would be 1, 2, 3, 4, 5, 6. Okay, so that's 6 of the electrons. Now we're down to 18. Okay, I see here that the oxygen on the left-hand side, far left-hand side, okay, wants to be involved in 2 bonds, but it's only involved in 1. So I could put a double bond there. Okay, that would take me down to 16. Okay, I see the nitrogen over on the, well, towards the right side of the molecule here, only has 2 bonds. It wants to have 3. So maybe we could put another pair there. Okay, gets us down to 14. We could put lone pairs here on the oxygens. So 2, 4, 6, 8. That takes us down to 6 valence electrons. Okay, the oxygen that's bound to the oxygen and nitrogen currently sees 6 electrons, so we could give it 2. It takes us down to 4. And the nitrogen here sees 1, 2, 3, 4, 5, 6. We can give it 2 electrons. And we still have 2 electrons to go. And I am stumped as to where we could possibly put these electrons. There's nowhere to go. So at this point, the only way that we could add them would be to break some rules. Okay, so we can say that, again, this is not plausible. Okay, now on the right hand side, far right hand side, we can put 6 electrons in where we've implied bonds. So that takes us down to 18 electrons to account for. Okay, I can see that nitrogen wants to have 3 bonds. It could have 4 bonds, but let's not worry about that yet. Let's say we want to put another pair of electrons on nitrogen to give us our octet, and that should be good. So I'm going to redraw this actually a little bit here. so we're down to 16 electrons that we're trying to account for. And we have 3 atoms. Okay, we have 3 atoms. 16 electrons divided by 3 is going to give us a strange arrangement here. So we could have maybe 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, so that's going to take us down to 4, and we wind up with an odd number of electrons on each one of the oxygens. Okay, but remember what I said back in the beginning, that the nitrogen can have 4 bonds. Not only that, oxygens want to have 2 bonds. So what if instead of giving the nitrogen the lone pair of electrons, what if I did this differently? What if I, again, started off with the 6 electrons here, but what if I made one of these NO bonds a double bond? Okay, so that's going to take us down to, let's see, that's 24 minus 8 is 16. Okay, now I know that this oxygen right here wants to have 8 electrons. So that takes me down to 10 because we just added 6 electrons. The same thing with this guy over here. So we had 6 from that, so that gives us 4, and then the last 4 can go here. Okay, and I'm going to draw this in kind of a tidier form. So here we have the Lewis structure for this, almost. Just like with what we saw in the cations, we still have to worry about formal charges. So what I'm going to do is I'm going to redraw the structure down here, and we're going to figure out the formal charges. And I think you're going to find that this particular compound is actually pretty interesting in the way the formal charges work out. Okay, so let's look at the formal charge on nitrogen first. Remember, the molecule itself has an overall -1 charge. Okay, so here, start with the number of valence electrons. Nitrogen should have 5 valence electrons, minus the sum of the non-bonding electrons, which is 0 for nitrogen. Okay, plus half of the number of bonding electrons. So this nitrogen is bound to 1, 2, 3, so it's involved in 4 bonds, each with 2 electrons. So that's 8 divided by 2. And we get a +1, which is weird, right? Because the molecule is supposed to have a -1 charge overall. How can I possibly have a formal charge of +1? Well, the only way we can really justify this is by going through the different atoms and see what works out. Okay, now, remember, we have to look at these 3 different oxygens individually. Now, I can already tell you that this oxygen and this oxygen are going to be equivalent to one another. Okay, they have the same number of bonding electrons and the same number of non-bonding electrons. But this guy over here is going to be different. Okay, so let's first do the formal charge calculation on the blue one. Okay, so this oxygen should have 6 valence electrons. The way that I have it drawn here, there are 4 non-bonding electrons. The oxygen's involved in 2 bonds with 2 electrons each. That's a total of 4 bonding electrons divided by 2. Okay, so 4 divided by 2 is 2 plus 4. 6 minus 6 is 0. Okay, so there's no charge on the oxygen, the blue one at least. And we know that there is a positive charge on the nitrogen. Now, the only way that this molecule could have an overall negative charge is if both of those oxygens that are green have a negative charge. So let's see how that works. Okay, again, we should have 6 valence electrons. Okay, now remember, we're only going to look at one of the oxygen atoms, not both of them, when we're counting the number of electrons. So each one has a total of 6 non-bonding electrons. Okay, each one has a total of 2 bonding electrons. So 6 plus 1 is going to be 7. 6 minus 7 is negative 1. So there you go. We have a negative charge on each one of the oxygens and a positive charge on nitrogen. Okay, so hopefully you can see there that it's important to go through all the formal charge calculations. In fact, you can have molecules that are going to have a net neutral charge, but still have a plus and a minus buried somewhere in there. So always make sure you carry out the formal charge calculation, even if it's not a cationic or anionic compound. Now, one last thing I want to look at with Lewis structures is how we're going to deal with exceptions to the octet rule. Okay, there are 3 major exceptions that we need to look out for. The first one is called the incomplete octet. Okay, we see this in a couple of different compounds. One example of this would be beryllium hydride. Okay, beryllium hydride got 2 valence electrons times 1 atom gives us 2 valence electrons from beryllium. And then for hydrogen, we have 1 valence electron times 2. That's 2 valence electrons. So we get a grand total of 4 valence electrons. Okay, and we already know that there is no, well, that you can't have an octet anywhere if you only have 4 valence electrons. The structure comes out to look something like this. Okay, and like I said, there's a couple of compounds or types of compounds that are capable of that. So just because you don't have a complete octet doesn't mean it's always wrong. But if you can draw a Lewis structure that has the complete octets, that's usually a sign that that is the correct structure. Okay, so if you have the choice between 2 structures, one where it's incomplete and one when it's full, go with the one where it's full. The second possibility is to have what's called an expanded octet. Okay, we see this mostly when we're dealing with elements that are in, let's see, the 4th row and down. Actually, no, 3rd row and down, because this is going to be possible only in cases where you have access to d orbitals. Okay, so we see this a lot in things like silicon and sulfur and phosphorus and the halogens. Okay, so one good example of this is a compound called sulfur hexafluoride. Which is not fun to draw. You can see here we have the 6 fluorines, and then each one of those is going to have their full complement of electrons. But if you look at sulfur here, you can see that there's a total of 6 bonds, each with 2 electrons, and that means it's a total of 12 valence electrons. And that's okay. Okay, that's because sulfur has access to its d orbitals. And again, we see this with other elements as well. And the last exception shows up when we have an odd number of electrons, or an odd number of valence electrons. Okay, and in this case, it's just not possible to have an octet. An example of this would be NO2. Okay, so we have nitrogen with its 5 valence electrons, oxygen with its 6, for a total of 17 electrons that we have to account for. Okay, we start distributing those 17 electrons. We get 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you can see that the octet rule for nitrogen is fulfilled. And 1, 2, 3, 4, 5, 6, 7, 8. So is oxygen, but we didn't have that 8th one, so let me take that off. Okay. Now, we could try drawing this a number of different ways, but at the end of the day, it's going to be short 1 electron. And you can't possibly have every atom having its octet if there's an odd number of electrons. So that's how we just basically have to deal with that. All right. Now there's other ways that we could have drawn this. We could have drawn it in a way that puts that unpaired electron on nitrogen. So that should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, and we could talk more about what that means probably a little bit later on in the chapter. Okay, but this is how we draw Lewis structures, and it's a very important concept. Please make sure that you practice this at the end of the chapter. There are plenty of practice problems. Okay.